What you're listening to now is an expert briefing on the family of systems commonly referred to in industry and press as the Musashi factory-class robots, a portfolio that sits at the intersection of Musashi Seimitsu's manufacturing heritage and the newer Musashi AI business unit, itself the outcome of collaborations and joint ventures combining Japanese industrial engineering with startup AI teams. The modern Musashi AI entity develops and commercializes automated visual inspection systems, autonomous material handling units, and related factory robots that are explicitly designed to be retrofitted into existing production lines. This business grew out of Musashi Seimitsu's long history as an automotive parts supplier together with partnerships that brought Israeli AI and robotics startups into the fold. As to when and how the Musashi factory robots were invented, the story is evolutionary rather than a single, eureka, moment. Starting from Musashi Seimitsu's manufacturing automation efforts and early trials with partner firms, Musashi AI emerged over the last several years as a product business focused on machine vision quality inspection and autonomous intralogistics. Public deployments, pilots and demonstrations, including installations at major OEMs and showings at trade events such as Automate and Vision, accelerated the productization process through 2020-2024. Turning research prototypes into commercial inspection units, autonomous forklifts and fleet solutions. The product family therefore reflects a steady commercialization path. Research right pointing arrow pilot right pointing arrow retrofit deployments right pointing arrow event demonstrations right pointing arrow commercial rollouts. The main features and specifications of Musashi's factory-class robots vary by model, but they cluster around a few core capabilities. Edge-deployed deep learning visual inspection, high-resolution cameras with convolutional neural networks trained to detect surface defects on complex parts, mobile autonomous platforms for material handling, autonomous forklift driving stacks, integrated fleet management software, and modular hardware that can be installed into different production cells. On the inspection side, specifications commonly advertised include multi-camera rigs, sub-millimeter defect sensitivity on many part geometries, real-time inference at the edge, and integration APIs for factory MES ERP systems. On the autonomous logistics side, typical specs include obstacle detection and avoidance for indoor environments, path planning for pallet tote movement, and safety-rated sensors to operate around humans. These systems are marketed as ready to use. Inspection stations are as fleetable AMR autonomous mobile robot units, often with the option of cloud or on-premise analytics dashboards. Structurally, Musashi's factory bots are purposely modular. Inspection machines are built around a rigid frame that holds cameras, lighting arrays, and a mounting surface for parts. Mobile robots generally use steel or aluminum chassis for strength and durability with industrial castings for the load-bearing elements. Enclosures and exterior panels typically employ industrial plastics or composite panels to reduce weight and avoid corrosion in factory environments. Connectors and racks are industry standard so the machines can be serviced quickly. Critical mechanical parts such as actuators and drivetrain components use hardened steel and sealed bearings to survive the dust, vibration and shift work of production environments. The design philosophy is industrial grade. Maintainability, serviceability, and compatibility with existing conveyor and fixture tooling are prioritized over bespoke, decorative finishes. How these machines work is a systems story. For inspection units, the core is a pipeline of controlled illumination, multi-angle high-resolution imaging, and an inference engine running trained deep learning models. Images are captured under calibrated lighting to remove specular highlights, then pre-processed and passed through convolutional neural networks, often customized architectures trained on defect-labeled datasets which output classifications or segmentation maps pinpointing defects. The system then flags parts, logs metadata, and can trigger downstream actions reject, rework, or route for human review. Sensors include industrial cameras, encoders for part positioning, and sometimes laser profilers for 3D surface checks. For mobile logistics robots, the stack includes lidar or depth cameras for mapping and obstacle detection, IMUS and wheel encoders for odometry, real-time path planners, and drive actuators, brushless DC motors with industrial motor controllers. AI components run both at the edge for latency-sensitive perception and in connected servers for fleet orchestration, while safety functions rely on redundant sensors and safety controllers to satisfy industrial safety standards. Actuation is handled by servo BLDC motors with closed-loop controllers. Pneumatic or electric grippers are used for manipulation tasks where needed. Price and estimated cost are not published as single retail SKUs because Musashi's approach is largely enterprise sales, customization and, in some cases, robots as a service. Historically reported business models include project-based deployments and rental usage pricing in markets with labor shortages, which can place the cost of deploying a robotic line at a fraction of hiring full-time human labor over a year. As a practical estimate, a turnkey vision inspection cell from an industrial integrator often runs from tens of thousands to low six figures USD depending on complexity. An AMR or autonomous forklift solution can similarly range from tens to hundreds of thousands per unit plus software, installation and integration. Many customers therefore compare lifetime cost and throughput gains rather than unit sticker price. Musashi's business literature emphasizes pilot projects and ROI calculations rather than list prices. The country of origin for the Musashi industrial lineage is Japan. Musashi Seimitsu was founded in Japan and much of the manufacturing and engineering heritage is Japanese, while Musashi AI's operations and go-to-market include international entities, for example a North America presence in Waterloo and partnerships globally. So the product family is best described as Japanese-rooted with international R&D and commercial footprints. Future benefits and applications for humanity focus on productivity, quality and safety. These robots reduce repetitive inspection tasks that are error-prone for humans, accelerate defect detection so fewer faulty parts reach customers, and free human workers from dangerous or ergonomically harmful tasks. In logistics, autonomous movers reduce workplace injuries, optimize material flow, and allow factories to scale throughput without linear headcount increases. At a societal level, these systems contribute to more consistent product quality, potentially lower manufacturing waste, and improved factory working conditions, especially in aging workforces or regions with labor shortages. Less known or hidden facts worth noting. Musashi's product family is not a single monolithic robot but a portfolio of purpose-built systems, and in industry press there is sometimes confusion between similarly named initiatives. For instance, the University of Tokyo's Humanoid, Musashi, a research robot demonstrated driving a microcar, is separate from the Musashi AI commercial inspection logistics products. Another often overlooked point is the business model innovation. Musashi and partner ventures have experimented with robot employment, or task-based pricing, essentially offering robots by the hour or by project, an operational model that changes procurement and financing for small and medium manufacturers. Finally, Musashi's emphasis has historically been on retrofit and integration, meaning many installations are hybrid systems that combine legacy automation with modern AI, rather than pure greenfield replacement. Looking toward possible future developments and impact, we can expect tighter integration between factory floor AI and enterprise systems, real-time quality feedback loops into design and supply chains, more widespread deployment of collaborative mobile fleets that coordinate via edge cloud orchestration, and ever better perception models that reduce false positives and broaden the range of inspectable part geometries. Ethically and economically, these developments will amplify productivity but also require careful workforce transition planning, upskilling and redeployment of human workers into supervision, maintenance and higher value tasks. If universities' humanoid experiments like the research Musashi that demonstrated vehicle operation continue, we may also see cross-pollination, research insights about human-like manipulation and perception being transferred into ruggedized factory platforms. In short, Musashi-class systems point toward factories that are smarter, safer and more resilient, provided industry, regulators and communities manage the transition responsibly. That completes a compact but comprehensive expert walkthrough of who built the Musashi factory robots and how they were developed, when and how they were introduced commercially, their principal features and structural choices, how they operate, realistic cost expectations, origins, societal benefits, lesser-known details, and plausible future trajectories. If you'd like, I can now produce a slide deck or a short video script based on this transcript that emphasizes any section you want to use in a presentation or YouTube video.